Hello! In this video, we are going to prove the theorem involving compositions of functions. And so here's how it goes. Suppose f is a function from a to b, and g is a function from b to c. Then, the composition of g and f is a function from a to c. And for any element a in the set A, we have that the functional value of g compose f at A is equal to g of f of A. So, we're first going to prove that g compose f is a function from A to C. Okay, so then what does this mean? Well, we have to think about what the definition of a function is. What we're really trying to prove is that for every element A in the set A, there is a unique element C in the set C, such that A comma C is an element of G compose F. So really, this is what we're trying to prove. So, because we're proving a statement involving every element in A, give me any element in A. We want to prove that there is a unique C in C such that A comma C is an element of G compose F. Now first we're going to prove that there exists a C in C such that A comma C is an element of G compose F. And then we're going to prove that it's unique. So we're going to start with existence. Now notice A is an element of A, and f is a function from A to B. What that means is f has a functional value at A. And we could say, for instance, let b equal f of A. And f is a function from A to B, so we know that b must be an element of B. Furthermore, now that we have b is an element of B, and we know g is a function from B to C, we know that g has a functional value at B. We could say, for instance, let C equal g of B, which we know is an element of C. So what these two things mean here is that A comma B is an element of F, B comma C is an element of G. Okay, so now it turns out that because A comma B is an element of F and B comma C is an element of G, it follows that A comma C is an element of G compose F. This comes from the definition of composition of relations. And so this proves that there exists an element in C such that A comma C is an element of G compose F. We have found one. So now we want to prove that this value C is unique. And so to prove uniqueness, we're going to assume that A comma C1 is in G compose F and A comma C2 is in G compose F. To prove uniqueness, we have to show that C1 equals C2, right? That's the idea. And so how should we start out by doing that? Well, notice we are an element of a composition. So by definition of composition of relations, we can choose some value, say B1, such that A comma B1 is an element of F, and B1 comma C1 is an element of G. And we can also apply that same idea to what we have here. We can choose some B2 such that A comma B2 is an element of F, and B2 comma C2 is an element of G. Okay, so now notice A comma B1 is an element of F, A comma B2 is an element of F. But F is a function, so A must map to a unique value. So we must have B1 equals B2. Okay, so since B1 equals B2, we could replace the B2 here with B1. So really, B1 comma C2 is an element of G. So in a similar way, we see that B1 comma C1 is in G and B1 comma C2 is in G. In the same way, since G is also a function, we know that B1 must also map to a unique element. So C1 must equal C2. Which is exactly what we wanted to prove, right? We were assuming that this is true and this is true. We wanted to prove that C1 and C2 were equal. And so this proves uniqueness. So at this point, we have proven that there is a unique element in C such that A comma C is an element of G compose F. And since A was arbitrary, this concludes that this entire statement is true. So we do in fact know that G compose F is a function from A to C. Okay, so we've proven this, but now we still have to prove that for any element A in set A, the functional value of G compose F at A is equal to G of F of A. So how do you suppose we show this? Well, since it's a statement regarding any element in A, just give me any element in A, right? I like that. That was good. We want to show that the functional value of G compose F at A is equal to this. Now, it turns out that the sequence of steps we're going to perform here is going to be basically identical to what we did in the existence portion. So really, because f is a function from A to B, we could let B equal f of A. Right? And just like what we did here, we could let C equal G of B. And as before, A comma B is an element of F, B comma C is an element of G. So by definition of composition of relations, A comma C is an element of G compose F. This is exactly what we did in the existence portion right here. But now that we know G compose F is a function from A to C, we can say that the functional value of G compose F at A is equal to C. But C is just equal to G of B. And since B is equal to f of A, we could just replace the B here with f of A. So we get G of f of A. So we can see that G compose F evaluated at A is equal to G of f of A. Exactly what we wanted to show. So this completes our proof, right? We have shown that G compose F is a function from A to C, and using that G compose F is a function from A to C, we are able to figure out what the value of G compose F is at A. It's G of f of A. So yeah, that's pretty much the whole idea of how you could prove a theorem like this, right? So yeah, that's pretty much it for this video.